Hello and welcome to the CCQTA Lunch and Learn series. I'm Dave Murray, Secretary to the CCQTA. We're using this series as an opportunity to engage with both our members and industry in general, to provide education on current topics of interest. Our first series focuses on vapor pressure, which has been an area of interest and a lot of activity for many years. This first episode aims to answer some basic questions about vapor pressure to ensure we're all on the same page. Just a quick note that crude oil is used generically to cover condensate, diluent, light and medium crudes, as well as diluted bitumen or dilbit. First, let's answer some basic questions. What is vapor pressure? What are the terminologies that are used for vapor pressure? And why does vapor pressure matter? Now, some of this may appear a little basic. However, it's important to make sure we're all on the same level before we get too far into this topic. So let's start with what is vapor pressure. The encyclopedia definition is vapor pressure is a measure of the tendency of a material to change into the gaseous or vapor state, and it increases with temperature. The temperature at which the vapor pressure at the surface of a liquid becomes equal to the pressure exerted by the surroundings is called the boiling point of the liquid. Now, to get a little more technical, the vapor pressure of a pure compound is the pressure characteristic at any given temperature of a vapor in equilibrium with its liquid or solid form. Vapor pressure is a measure of the ability of a compound to bond with itself. Compound molecules that tend to bond well with each other have a low vapor pressure, meaning less tendency to escape into the vapor phase, while poorly bonding compounds will have a higher vapor pressure, meaning a greater tendency to escape into the vapor phase. Now, to get even more technical, from a thermodynamic standpoint, this can be viewed from the well-known Clausius-Clapeyron expression, where delta H is the heat of vaporization. So in explanation, the energy needed to break intermolecular bonds in the pure condensed liquid. Since breaking bonds requires the input of energy, we would expect the vapor pressure of a compound to increase with increasing temperature. So how does vapor pressure relate to evaporation and boiling? An important distinction between evaporation and boiling is that evaporation is a surface phenomenon, while boiling is a whole fluid phenomenon. When the vapor pressure is below atmospheric pressure, evaporation takes place because atmospheric pressure is pushing on the surface, preventing bubbles from forming. When the vapor pressure is above atmospheric pressure, boiling takes place throughout the fluid because bubbles can form. Keep in mind, even ice has a vapor pressure, which is why ice cubes left in the freezer shrink over time. There is also a difference between an open and closed system. In an open system, the vapor pressure allows molecules from the surface to evaporate and enter the vapor space above the liquid. However, these molecules can escape, so equilibrium cannot be established. Therefore, evaporation continues. On the other hand, in a closed system, such as a sealed tank or cylinder, evaporation also occurs. However, the molecules can't escape, so they reach an equilibrium where an equal number of molecules evaporate as do condense. A floating roof tank would be a hybrid of these two, where it is a closed system. However, there are small losses that occur around seals, fittings, etc. How about for a complex mixture like crude oils? Let's look at this in practical terms. Crude oil has hundreds to thousands of individual components with widely varying characteristics. However, only the smallest components have appreciable vapor pressures. This is because the smaller the molecule, the lower the intermolecular forces, so they don't want to hang around together. Now let's look at the vapor pressure of these components as a function of their size. On the y-axis, we have the molecular volume or size, and on the x-axis, the carbon number from carbon-1 methane through carbon-6 hexane. The size of the bubble represents the vapor pressure contribution of each component. For example, C6 has the largest molecular volume, but the smallest vapor pressure at 40 kPa. Conversely, C1, methane, has the smallest molecular volume, but has the largest vapor pressure at a whopping 35,000 kPa. Let's look at why this is. Let's look at methane, pentane, and heptane, and how they interact with themselves. These ball and stick diagrams depict the individual carbons and the bonds between them. The hydrogens are assumed on each carbon. There are 3 isomers of pentane and 9 isomers of heptane. These are the different configurations using the same number of carbons. Let's go ahead and compare how pentane isomers will react with each other. N-pentane is basically a straight chain. Stacked on top of one another, they can get quite close to each other, allowing their hydrogens to interact, resulting in hydrogen bonding. In this case, they have 5 points of close interaction. If we take isopentane, the methyl group sticking up from carbon 2 restricts how close the other atoms can get to one another, meaning the intermolecular bonding will be far less than that for N-pentane. Now let's take a look at heptane. We'll only look at two isomers. N-heptane is very similar to N-pentane in that it's a straight chain and it has up to 7 areas of potential interaction. This branched chain version interacts similar to isopentane, except it has multiple branches, so it can't get close enough geometrically to allow close interaction. This chart is a good illustration of the effect carbon number has on the boiling point and how the boiling point is also related to the vapor pressure. You can see methane has a very large vapor pressure bubble, which also means it has a very low boiling point at minus 161 degrees Celsius. Hexane, on the other hand, has a small vapor pressure bubble and a much higher boiling point at 69 degrees Celsius. The orange line represents an ambient temperature of 20 degrees. You can see on the plot that C1 and through C4 all have boiling points well below ambient temperature, so at atmospheric pressure they will boil throughout a fluid and not just from the surface. In a closed system, these components will reach equilibrium with the vapor space provided. Now that we know we have molecules in the vapor space, we need to determine how much the individual component vapor pressures contribute to the overall vapor pressure. In steps Dalton's law of partial pressures. Dalton's law of partial pressure states the total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual component gases. The partial pressure is the pressure that each gas would exert if it alone occupied the volume of the mixture at the same temperature. As the previous chart showed, in crude oils, C1 through C6 are the largest contributors to vapor pressure. Therefore, this is also what we find in the vapor space above the liquid. The molar concentration or mole fraction of each, as per Dalton's law, is what determines the overall vapor pressure. Let's look at a real example of a crude oil. On the right, you can see that C1 through C10 make up about 34% of the total mass of the sample. Let's look at the impact of this on the vapor pressure. This chart represents the composition. As with the previous chart, the size of the bubble represents the vapor pressure contribution of each component. Comparing the concentration of C4 versus C1, C1 is only a fraction of the concentration of C4, but the vapor pressure contribution is almost the same. Take C8 as well, which has close to 7% of the overall concentration, but only contributes 0.25 kPa to the overall vapor pressure. As per Dalton's law, the vapor pressure contribution of each of these add up to the overall vapor pressure, which in this case is 85 kPa. What is interesting is that 74 kPa comes from C1 through C4 and only 11 kPa comes from the C5 plus fraction. At 20 degrees C, that means the bulk of the vapor pressure contributing components are boiling and vulnerable to rapid loss. Let's summarize what we've learned so far. Low carbon numbers have high vapor pressures and low boiling points. High carbon numbers have low vapor pressures and high boiling points. At typical ambient conditions, there's an opportunity for both boiling as well as evaporation from a crude oil. C1 through C6 are responsible for the bulk of vapor pressure contribution in crude oils. Open vessels experience evaporation and loss. And finally, closed vessels experience no evaporation and loss, except in the case of a floating roof tank, which is a bit of a hybrid, as we've discussed already. Now let's move on to vapor pressure terminology. The most commonly used terminologies are true vapor pressure, TVP, total vapor pressure, also TVP, and lastly, reed vapor pressure, RVP. Why are there so many? Let's look at how vapor pressure is defined throughout the industry. ASTM D4175 is the terminology standard for the ASTM D02 Committee on Petroleum Products, Liquid Fuels, and Lubricants and attempts to gather and standardize definitions between all the various associated standards. So looking at these four, the first one is vapor pressure generically, the pressure exerted by the vapor of a liquid in equilibrium with the liquid. Okay. Total vapor pressure is observed pressure measured in the experiment, that is the sum of the partial pressure of the sample and the partial pressure of the dissolved air. True vapor pressure here, the pressure at which the fluid is in equilibrium between its liquid and gas state. And the last one, vapor pressure of crude oil, VPCRX, is the pressure exerted in an evacuated chamber at a liquid vapor ratio of X to 1 by conditioned or unconditioned crude oil, which may contain gas, air, or water, or a combination thereof, where X may vary from 4 to 0.02. Now, while not incorrect, the TVP definition here is open for interpretation because it does not specify the vapor-to-liquid ratio. As we saw in previous definitions, the TVP is where the vapor-liquid ratio is 0 to 1. ASTM D4057 is a sampling practice, so it should be more clear on the definition, so it would be better if they clarified that further. The reed vapor pressure, or RVP, is well known since it was first published back in the 1930s. It states the resultant total pressure reading, corrected for measuring error, of a specific empirical test method, ASTM D323, for measuring the vapor pressure of gasoline and other volatile products. The equilibrium pressure exerted by an air-saturated fluid at a 4 to 1 vapor-liquid ratio at 37.8 degrees Celsius. Notice the scope of the definition here. Gasoline and other volatile products. The standard was intended for finished product and mostly for fuels that may experience vapor lock in carbureted engines. The VL of 4 to 1 was used so that air saturation of a sample stored in an open container would not impact the overall vapor pressure measurement. Let's look at the true vapor pressure as the US EPA defines it. As per EPA AP 42 Chapter 7. It states true vapor pressure is defined in various ways for different purposes within the industry, such as bubble point for transportation specifications, but for the purposes of these emissions estimating methodologies, it is the sum of the equilibrium partial pressures exerted by the components of a volatile organic liquid using Raoult's law. True vapor pressure may be determined by ASTM D2879 or D6377 for crude oils with a true vapor pressure greater than 3.6 psia, or obtained from standard reference texts. For certain petroleum liquids, true vapor pressure may be predicted from reed vapor pressure, which is the absolute vapor pressure of volatile crude oil and volatile non-viscous petroleum liquids, as determined by ASTM D323 or 5191. Note the use of absolute vapor pressure here, which serves to further confuse the issue. From the text, it sounds like it would be equivalent to true vapor pressure as we've discussed. However, it is actually the same as RVP, which is air saturated at 4 to 1 VL. This definition of RVP is also not consistent with D323 itself. EPA also indicates that D2879 or D6377 can be used. However, the VL ratio of 2879 is 0.4 to 1, so a 40% ullage, and the statement does not indicate if D6377 also needs to be at a 0.4 to 1 to be equivalent. Also note the point that for certain petroleum liquids, TVP may be predicted from RVP. What petroleum liquids is this referring to? One could potentially assume crude oil since it's mentioned in the description, but it's still a little ambiguous. Let's look at another EPA definition. This one states, true vapor pressure means the equilibrium partial pressure exerted by a petroleum liquid as determined in accordance with the methods prescribed in API Bulletin 2517, evaporation loss from external floating roof tanks. Here you can see that even EPA uses different definitions within its own documents. Here's another definition, this one from the International Maritime Organization, which is the UN specialized agency with responsibility for the safety and security of shipping and prevention of marine and atmospheric pollution by ships. It states the true vapor pressure or bubble point vapor pressure is the equilibrium vapor pressure of a mixture when the gas-liquid ratio is effectively zero. It is the highest vapor pressure which is possible at any specified temperature. As the temperature of the petroleum mixture increases, its TVP exceeds atmospheric pressure, where the liquid commences to boil. Now, this is probably the best definition of true vapor pressure, with the least ambiguity. It specifically indicates the VL ratio it's based on and is consistent with the theory of vapor pressure. A floating roof tank where the roof is floating directly on the oil would meet this TVP criteria. Lastly, total vapor pressure. The only difference here is the total vapor pressure of a crude oil is the equilibrium partial pressure exerted by all the individual components, including the partial pressures of all hydrocarbons, plus the inclusion of the fixed gases such as carbon monoxide, carbon dioxide, hydrogen, hydrogen sulfide, nitrogen, and oxygen. Effectively, this is what is measured using D323 or D6377 test method, since it's possible for fixed gases to be present in a crude oil. Well, now that we've blown your mind with all this terminology, let's try to summarize this. To summarize in practical terms, true vapor pressure is equal to the vapor pressure at a VL of 0 to 1, which is also the bubble point. VPCR, based on D6377, has a condition that the VL ratio is 4 to 1. Therefore, TVP does not equal VPCR4, and subsequently TVP will be greater than VPCR4. RVP, based on D323, is also measured at a VL of 4 to 1. Therefore, RVP also does not equal TVP, and TVP will be greater than RVP. Now, based on D6377 section 1.x1.2, multiplying VPCR by 0.834 for pressurized samples or by 0.915 for non-pressurized samples, the RVP can be predicted. This indicates that the VPCR4 should also be greater than RVP. This is true in most cases. However, we will get into the details of why they can be the same in another episode. Let's look at one last chart showing how the various terms would be interpreted. This is an example of a phase diagram of a generic crude oil. If you're not familiar with a phase diagram, the upper line equals the bubble point, while the lower line equals the dew point, all as a function of pressure and temperature. The center of the diagram is the two-phase region depicting the various VL ratios. This illustrates the pressure where the TVP appears versus where the VPCR4 appears. That explains why there's quite a significant difference between the two, which is why terminology matters when discussing vapor pressure. So you can see on the chart there's a significant difference between one pressure and the other. Which term should be used? When referring to ASTM D6377 results, the proper term is the VPCRX TM, where X equals the VL ratio and TM equals the temperature, since either could be different. A VL of 4 to 1 at 37.8 degrees C or 100 degrees Fahrenheit is the most common, so reporting as VPCR4 37.8 degrees C is the appropriate term. When referring to ASTM D323, the proper term is RVP, since the conditions of the read vapor pressure are clearly defined. An important takeaway is that terminology matters because there are implications behind names and acronyms that can easily be confused. Referring to D6377 as TVP is not appropriate. On to the last question we posed. Why does vapor pressure matter? For one, safety. Another, operational concerns and issues. And lastly, the environment. All three are impacted by vapor pressure. Let's start with safety. Both employees and the public are at risk of exposure to inhalation risk as an asphyxiant, overpressure conditions on rail cars or tank trucks leading to venting, floating roof tank instability, flammability and or explosion risk during accidental releases, such as derailment, road accidents, spills, venting, etc. Now let's take a little bit closer look at these. Let's start with flammability. Ignitability and flammability are related to the ratio of fuel vapor to air. When the ratio of hydrocarbons to air is in the appropriate range, the air-fuel mixture will ignite in the presence of an ignition source, such as a spark or static release. There is both a lower and upper explosive limit. The following plot helps to visualize the explosive range of each of the most volatile hydrocarbons we've been looking at. This plot shows the range where each component is explosive when mixed with air. Keep in mind that beyond the upper limit, there's not sufficient air to ignite the fuel and support combustion, or in other words, the mixture is too rich. You can see that C1, or methane, has a very wide explosive limit from about 4.4 to about 16.2% volume in air. So very large, and this gets slightly smaller with each individual carbon number. But again, they all have a fairly broad range, so it doesn't take a whole lot of hydrocarbon in air to be explosive. Let's look at some incidents related to safety. The first is a refinery reporting receiving rail cars at 172 kPa, so about 25 psi at offload. The observation they made was like oil was boiling over the top of the car like a soda can. Now you imagine the atmosphere near that rail car as volatile material is boiling out, and the likelihood that an explosive mixture in the air was present. At that point, a simple static discharge could have resulted in an explosion. The next type is floating roof tank failures. There have been several reports where high vapor pressure crudes have resulted in flipping the roof, where the internal vapor pressure exceeded the atmospheric pressure plus the weight of the roof and lifted the roof off some or all of the liquid, resulting in destabilization. Keep in mind, when the floating roof tank flips, all of the vapor that's sitting in that space is released into the air, forming a potential explosive mixture above and near the tank. Now, another example is a truck driver who's been hauling crude oil and is bringing back an empty trailer containing a small amount of residual crude. If that was high vapor pressure crude, it's possible that when the tank hatches open, the atmosphere inside the tank is full of hydrocarbon. Well, the gas mixture inside the tank is likely too rich to be explosive. As soon as the hatch is opened, the gas from inside begins to interact with the air, potentially forming an explosive mixture above the hatch. There is also a danger that the hydrocarbon gases inside the tank displace the air, causing an asphyxiation hazard to any nearby workers. The last example of incidents related to safety is the Lac-Mégantic, Quebec train derailment disaster in July 2013. In this case, the volatility of the light Bakken crude oil involved is implicated in the size of the explosion and the subsequent fires. Overall, the ruptured railcar spilled 6 million liters of light crude, as well as killed 42 people, plus injured countless others. Now let's look at operations. There are also operational considerations to vapor pressure. Pipeline systems have specifications for which they were designed, and transporting high vapor pressure product may exceed those specifications. Now, pipeline tariffs are also unique to the operator and may include parameters such as vapor pressure. Then we have system volume losses. Earlier we talked about breakout tankage on some lines while others are tight line. In the case of systems with breakout tankage, losses compound with each tank the product enters depending on the tank configuration and the time in tankage before moving on. So as the product moves further down the line, more and more losses occur as light ends are lost, so volume contracts. Lastly, pumps and meters in a transmission pipeline system are intended for single-phase product, and if a high vapor pressure product generates a vapor phase through pressure changes or temperature changes, then cavitation may lead to pump damage, and lastly, meters may not report correctly. Let's look at the environmental considerations. Volatile components or high vapor pressure are lost easily and quickly to evaporation even when the fluid does not appear to be boiling. This is especially true of methane, ethane, propane, and butane, which are normally gases at ambient temperature. Crude oil kept in storage tanks will evaporate or weather depending on the ambient temperature and the composition of the crude oil. This evaporation results in potential emissions, and this is where environmental concerns arise in relation to vapor pressure. In Canada, emissions guidelines are administered by the Canadian Council of Ministers of the Environment, or the CCME. Through PN 1180, the guideline for controlling emissions of volatile organic compounds from above-ground storage tanks. In the United States, emissions are administered by the Environmental Protection Agency and specifically EPA 40 CFR. CCME PN 1180 states all tanks with capacities greater than 75 cubic meters storing volatile organic liquids with a vapor pressure greater than or equal to 76 kPa shall have a vapor control system. A vapor control system means that it shall recover the vapors, destroy the vapors by thermal oxidation, burning, or other means, or recycle the vapors for other uses in the facility. The system shall prevent vapors from being emitted into the atmosphere with an efficiency of at least 95 weight%. Let's look at the highlights of the US EPA 40 CFR. I'm going to paraphrase a bit here. If the TVP is greater than 10.3 kPa but less than 76.5 kPa, then the storage vessel shall be equipped with a floating roof, a vapor recovery system, or their equivalents. If the TVP is greater than 76.5 kPa, then the storage vessel shall be equipped with a vapor recovery system or its equivalent. Note that the EPA uses true vapor pressure in their standards, so it's important to understand what they define TVP as. In this case, D6377 is acceptable, however they don't specify the VL, so they have left it open for interpretation. Since they also indicate RVP can be used, a VL of 4:1 could be interpreted. However, they also indicate that RVP should be used to predict the TVP, using the API nomograph. In this case, the VPRC4 could be used in place of the RVP and the TVP calculated from there. Let's see what that looks like in terms of measurement using the TVP to RVP conversion using the API nomograph. This is a version of the API nomograph that was developed in the 1950s and has been used for tank emission estimates ever since. It uses the read vapor pressure at a given temperature and converts it to TVP as the EPA defines it. This illustration shows a few examples of how the nomograph is used at various RVP values, all at 100 degrees Fahrenheit or 37.8 degrees Celsius. So here's the first one at 75.8 kPa converts to a TVP at 107 kPa. Next we have 82.7 kPa converts to 121 kPa, so we're well above atmospheric pressure. 89.6 kPa converts to 138. And finally, we have 100 kPa, so just under atmospheric pressure for an RVP, converts to a TVP of just under 160 kPa. Now, how would this be impacted by RVP measurement when it comes to emissions calculations? What if the VPCR4 was used to predict the RVP first and then used? Then you would be using a correlation on top of a correlation, which seems like a bad idea. Let's have a look at how tank emission estimates are impacted by vapor pressure. For the purpose of this example, I used RVP values and estimated the TVP from the API nomograph we just looked at. I ran emission estimate calculations at the various TVP levels using the EPA Tank 4.09D software. These represent 4 RVP conditions and their associated estimated TVP with the calculated annual tank roof emissions. This data highlights the sensitivity of emissions based on the measured results. You can see that for each PSI of TVP, the emissions increase by about 3,000 pounds per year. If there are issues with sample handling or measurement, then typically the results are biased low, so emissions would also be misreported as lower than actual. Now consider the EPA also allows the use of D6377, however, VL unspecified, to be used directly as a TVP. How would those compare? What is the impact of other factors on measurements? We'll look at those considerations in a subsequent episode. So let's summarize. Vapor pressure is simply a proxy for the concentration of small hydrocarbons that are emitted, which is what is actually of interest for emissions, toxicity, flammability, etc. The measurement method matters since different test methods give different results. For example, they have different VL ratios and temperatures. Emissions calculations are impacted by the measurement method, and really the best measurement method for emission calculations would be to use the actual composition of the material. The EPA primary definition of vapor pressure uses the composition and Raoult's law and is based on the true vapor pressure of the individual components in their relation to the mole fraction of the mixture. So ideally, a compositional measurement would be best. Let's leave the technical aside for a moment and just talk about how the CCQTA got involved in this. In March 2012, TransCanada did a presentation to the CCQTA titled Redevelopment of the TVP-RVP Correlation for Western Canadian Crudes. One of the reasons vapor pressure was in question was due to tank emission estimates and the impacts of measurement on the calculation/estimation of TVP. The presentation highlighted the various methods used for vapor pressure measurement, D323, D323M, and D6377, and that they produce different results for the same crude. TransCanada championed this work because the Keystone Pipeline is a tight line, meaning it has no breakout tankage between Hardisty, Alberta and Cushing, Oklahoma. This posed a problem because the endpoint is significantly warmer than the start point, so the vapor pressure has an impact on warmer operations and tank emissions. What was stable in Hardisty at 20 degrees C was not necessarily stable at 35 to 40 degrees C in Cushing. As was seen in the previous slide, small changes in RVP impact the estimation of TVP. What the presentation also questioned was the applicability of the API nomograph to current crudes versus the crudes from which it was derived back in 1959. This was also not the first time these issues were brought up. Bob Faulkner, who was with Imperial Oil at the time, brought this issue to the CCQTA's attention way back in November of 2000, citing similar concerns around both the test method as well as the use of the API nomograph. At the time, there was not sufficient interest within the CCQTA to initiate a project, so the topic sat dormant until TransCanada brought the issues back up again in 2012. This is a condensed timeline of events that took place over the course of the CCQTA TVP-RVP project. However, I'm only highlighting the first few milestones so as not to give away all the details to come. At this point, enough attention had been drawn towards the vapor pressure issues that API, through the Seeley Committee, requested EPA to approve D6377 for true vapor pressure measurement. Using D6377 bypasses the API nomograph and allows the result to be used directly. However, as I mentioned previously, there is an ambiguity in the EPA TVP definition in that it does not specify the VL ratio for D6377. I would suggest, in many cases, that D6377 is being used in place of RVP in the nomograph, and the actual TVP is still reported from the nomograph. Where did the project progress from here? The original project objective was focused towards a redevelopment of the correlation between the crude RVP and TVP, which is currently described by the equation/nomograph published within the API MPMS Chapter 19.2. The accuracy of this correlation for current market crudes has been viewed with increased scrutiny due to the view that the nomograph and related equations were thought to be originally developed on weathered/dead crude oils with little to no documented data on how the tests were conducted and the correlations formulated. Furthermore, due to the sample collection and air saturation steps dictated within D323 RVP method, it is believed that this testing procedure is highly prone to error through light and loss for blended and recent shale/tight crudes on the market today, or live crudes. The initial project scope was very broad and did not have a very specific direction. It was to gain an industry and regulatory consensus toward an accepted definition for crude oil true vapor pressure. At this point, TransCanada stepped in and committed significant effort and funding to begin to narrow the scope. Their initial work focused on comparing the various existing sampling and testing methods and presented those results to the CCQTA. That led to the revision of the scope. The revised scope was to develop an accepted method or methods for direct determination of true vapor pressure for transport quality crude oil over a range of temperatures. Also, no further attempts were going to be made towards correlating RVP to TVP, as well as no more attempts were going to be made towards justifying the validity of the current API Chapter 19.2 nomographs. Now, with all of that, I think we're going to leave it there for this episode. Coming soon, Episode 2. Episode 2 will do a deep dive into measurement and specifically into two areas: sampling methods and testing methods. Now keep checking the CCQTA website for the release date of the next episode. Thanks for watching, and I look forward to connecting again in Episode 2. If you'd like further information about this topic or any other topics the CCQTA is currently working on, please visit our website at CCQTA.com. If you have any specific feedback, please send it to secretary@ccqta.com.